All right. So I apologize about Monday. I had some things to take care of with the snow and everything. But I did give you yeah, there was an assignment, and with the assignment, yeah, there should have been a video, just a quick video on tangent. I know some of you guys were saying that you're having there was a little confusion with the lesson on the graphs of other functions, trig functions. So I gave you the video on tangent just to kind of give you another viewpoint on the subject. But I wouldn't worry about that too much right now, as long as you understand the sine and cosine, and as long as you have a kind of general grasp on how tangent works. The other ones, secant, cosecant, and cotangent, like I said, you're not going to be encountering them too often, unless you go into college and you start dealing with, trigonometry for your major, whether it's, some sort of science or something like that. All right. So today and for the rest of this week, we are going to be talking about inverse trig functions. Now, like any other function that we apply to variables and to numbers, most of the time there is an opposite operation that we use to work backwards, right? We have the square root and x squared, right? Those are inverse operations. They do the opposite thing of another, right? To put it in very basic terms, not very mathematical. So, right, for our trig functions, sine, cosine, and tangent, we have inverse trig functions as well. Now, before we get into the main things, I want us to think about the graphs. All right. So remember, for our graphs of inverse functions, let me just graph two basic ones first. No, that is not what I want to do. Give me 1 second. Sorry, guys. Right. So for our basic functions on the graph, they are reflections over the line y equals x, right? So this blue line here is y equals x. So the green line is x squared, which gives me my parabola. And then the purple line is the square root of x. Now, for our inverse functions, we do have to take in consideration things like domain and range. So you notice here, it isn't a true 100% reflection. Okay, the parabola, is a full parabola. It goes, left and right. It increases on two opposite sides. Our square root function is only half of that because there is a restriction on what we can plug into the square root function itself, right? We cannot plug in negative x values. We cannot have a range of negative y values, okay? It doesn't make sense for the square root. If I wanted a true reflection, I'd have to add the negative square root of x, right? So that would kind of complete the picture, and I'd need two functions for that, right? So for sine is, no, it's not. Sine is special because, or all these trig functions are special because, again, it's periodic, right? So if I zoomed out as far as I could, I'd have a squiggle line that went on forever, right? All the way to 500 there, it keeps going. Now, the problem I encounter, or that we encounter here, is when we do the reflection. This takes this horizontal squiggle line, and it would turn the whole thing vertical. But we can't have that. If I had a vertical squiggle line where this, went back and forth, it would no longer be a function, right? Our function, it would pass it would fail vertical line test, right? We would have more than one y value for one x value, right? Plugging in 0 would get us an infinite amount of answers. So we have to have somewhat of a restriction on the inverse. So just to show you, the inverse is only going to be a little squiggle. And I should have a better color than blue. Can I change the colors? I can't change the colors. Okay, we won't use that one. Right, so it's just this little squiggle here. And that is because of our restrictions. Right? So the same thing happens. I wish that was for our cosine function and our arc cosine function. Now notice our squiggle's in a different spot. And then tangent is a special case because here's our tangent, right? We talked about it looks like a cubic function, but repeated infinitely on both sides. The inverse tangent function would just be one, right? One line going across like that. So one thing you might have noticed is how we label our inverse, right? So we throw the word arc in front, and that means the inverse of sine. All right, so let's get down to it. So we'll start with the most basic. The sine. And so the inverse of sine is defined by the arc sine. So we say the arc sine of x equals y if and only if the sine of y equals x. So they have to be interchangeable like that. Right? So notice there we have the variable switched, right? Which means that we have the inverse. Right? So we do have some restrictions. So here my x is here. So for arc sine, I have a restriction on the x's, which is the restrictions on my sine, right? When I have sine, the range of my sine is from -1 to +1. So remember, when we take the inverse, we swap the domain and the range. So because the range of normal sine, I mean, it's, our original sine is from -1 to 1, then the domain of arc sine has to be from -1 to +1, right? So that's one of the reasons why our graph looked so funky. So I'm only allowed to plug in values into arc sine from -1 to +1. That's why I only have this little squiggle and it doesn't go on. Because once I go past -1 here, if I kept going, well, I couldn't plug anything in here, and it would just start repeating. It would come back in on itself. Again, not being a function. Okay. We also have a restriction because of the graph on our y, which is a little different here. Right? So our range for our arc sine is going to be from -π/2 to +π/2, or from -90 degrees to +90 degrees, right? If I went all the way to the end there, it tells you π/2, right? Which would be about 1.58 something. It just jumps there, right? And negative. Okay, So normally we don't have a restriction on what we can plug into sine. But when we're dealing with arc sine, our answers are going to be in between negative 90 degrees and positive 90 degrees. Okay? And when we start going into examples, most of the time we use this with triangles. And you'll see why. Because triangles, if we're dealing with right triangles, our triangles angles will be in between 0 and 90 degrees. All right, so there's two ways of showing inverse. So we have the arc sine, like we just saw. Or sometimes you'll see a sine with a -1 exponent. I like using this one because it's quicker and because that is the button that you see on your calculator, right? So those are your inverse operations. Word of warning. Having this doesn't mean that. Okay? This is something else. This is the cosecant. All right? So you can't do that when you have that, right? Right? The cosecant is 1 over sine. That's an x, right? So this, you'll just hear me say either sine -1 or inverse sine. Right? Or if it's written like this, I'll say arc sine. Excuse me. Any questions so far? I know this is pretty different than what we've seen. I'm not sure if you went over this in Algebra 2 at all. Okay, so how to use this, when we use this, there's a few ways. Okay, so one thing that we can do is if we're dealing with numbers that look familiar for our trigonometry, okay, we can use inverse properties of methods that we used before. So for something like this, I thought I had it up. I guess I don't. Okay. For something like this, we could use the unit circle. So this is saying, right, so if I set it up like this, where arc sine of 1/2 equals y, right, that's what we're looking for. We're looking to calculate some number y. Well, then I can imply this definition here, right? So the arc sine of something is y if the sine of that is what you're taking up, right? So what this is saying, right, and these are interchangeable, is the sine of what will give us -1/2. Right, so we take a look at the unit circle. Now remember, the sine is the y coordinate. So I'm looking, where is my y coordinate and -1/2? So as I go around the unit circle, here I have +1/2. Here I have +1/2. Oh, well, here I have -1/2, and here I have -1/2. But we have an issue. 7 pi over 6 and 11 pi over 6 are outside of our range, right? Remember, our range has to be in between negative pi over 2 and pi over 2, right? Or negative 90 degrees and positive 90 degrees. So what we can do is I can pick this one here, 11 pi over 6, and I can go in the opposite direction, right? So I can find a coterminal angle. So I have 11 pi over 6. Now, I don't want to add 2 pi to it because that would get me an even greater radian. So I'm going to subtract 2 pi from it. So we get negative pi over 6. All right, that is within our range, so that's good. All right, so again, we could double check. If I calculate the sine of negative pi over 6, well, that's going to get me negative 1/2. Right? Let's just do that real quick. Okay, here I'm in degree mode, so we're dealing with radians. So always make sure you change over. So now I'm in radians. It says RAD. So I'm taking the sine of negative pi over 6, and that gets us negative 0.5, negative 1/2. Right? Let's try using the calculator. So I want to find arcsine of negative 1/2. So for this, for whatever calculator you have, I can't find my graphing one right now. Okay, you're going to hit the second button and then whatever one you want, all right, and you'll see it pop up like that. And now I'm going to type in, I'll do negative 0.5, not 0.05, 0.5. Now this gets us a crazy negative 0.52359. Let's calculate this real quick. Negative pi over 6. That's the same decimal. Okay, so there's a slight drawback to using the calculator. I mean, it's a lot quicker. It gives you an exact answer. But if they're looking for a degree, right, let's see what happens real quick. This is in radians, obviously, right? So radians, that's a little tricky. And I wouldn't know to make negative 0.52 this into pi over 6, right? I don't know that there's that connection. So let's see what happens if I'm in degrees. So if I do the inverse sine of negative 0.5, there we go. This would be negative 30 degrees. Oops. Right? Which is what negative pi over 6 is. If I converted pi over 6 into degrees, it would give me 30. Okay, any questions so far? All right. So just as a heads up, we only have 5 minutes left. I'm not going to go over anything crazy. If I gave you something like this and I said to find the inverse sine of 2, well, right away, we would know that there is no solution. Okay, for a few reasons. Well, because my domain, remember, is -1 to 1. And let's see what happens if we plug it in. We get a domain error, right? Because there is no number that I can plug into sine to get me 2 as an answer. All right, so you have to make sure you're plugging in a number less than 1. Or more particularly, in between -1 and +1. All right, any questions about the sine? Or I should say arc sine. All right, so tomorrow we'll talk about cosine and tangent. They do behave similarly, but I will go over the specific definitions and rules, and then we're going to actually use these to solve for triangles. Okay, so now we're kind of getting a full picture of our right triangles, right? And then we'll be even able to take it further and deal with triangles that are not right triangles. All right, so for homework tonight, I'm going to give you 1 or 2 problems where you have to calculate. All right, use your calculator if you'd like. Try to use the unit circle if you can. If you're lost, if you get stuck on that, obviously you have the calculator. And then you can also check your answers with the calculator as well. All right, so it'll just be a quick couple problems where you just have to evaluate. All right. I will be nice on you, and I will let you answer in degrees or radians. Okay, most of the time we deal with radians, right? So for this, again, if you're in degree mode, this would get us -30 degrees, but because we're in radians before, we had -π/6. All right, so keep an eye out for that assignment, and I will see you all tomorrow. Have a good day.